Resistors in series and parallel. Here is a simple series circuit with two resistors, resistor 1 and resistor 2, in series. I've put a voltmeter VT for the total potential difference across the power supply and voltmeters across each resistor. I've also put 3 ammeters around the circuit. Now, for a series circuit, we know that the total potential difference is equal to the sum of the individual component potential differences. But we also know from Ohm's law that potential difference is equal to current times resistance. And so we can write that the total current times the total resistance will be equal to the current through resistor 1 multiplied by resistor 1 plus the current through resistor 2 multiplied by resistor 2. All I've done is simply used IR in place of the V's in this formula. But as the current is the same all the way round a series circuit, we know that the total current will be equal to the current through resistor 1 and also equal to the current through resistor 2. So we can cancel throughout by I to get the total resistance is equal to resistor 1 plus resistor 2 plus any other resistors that would be in the circuit. As a quick check at the end of a calculation, the total resistance will always be larger than the value of the largest single resistor in the circuit. Now let's look at this parallel circuit. Again, I have two resistors, resistor 1 and resistor 2. I've got a voltmeter to read the potential difference across the supply, the total potential difference, and the potential difference across resistor 1 and resistor 2. I have an ammeter measuring the current passing through the supply and down here, and an ammeter measuring the current that goes through resistor 1, another ammeter measuring the current going through resistor 2. We know that the current is shared between the branches of a parallel circuit, and so we can write that the total current, that running through the supply, will be equal to the current through resistor 1 plus the current through resistor 2. But from Ohm's law we know that current is equal to potential difference divided by resistance. So substituting in for potential difference over resistance in this formula gives us the total potential difference divided by the total resistance is equal to potential difference across resistor 1 divided by resistor 1 plus the potential difference across resistor 2 divided by resistor 2. But the potential difference is the same across each branch of a parallel circuit, which we can write as the total potential difference is equal to the potential difference across 1 and equal to the potential difference across 2. This means we can cancel out the V's to get that 1 over the total resistance is equal to 1 divided by resistor 1 plus 1 divided by resistor 2 plus any other resistors up to 1 divided by the nth resistor. We must not forget to invert at the end to get the total resistance. In a parallel circuit, as a quick check at the end, the total resistance will always be less than that of the smallest resistor in the circuit. Let's look at a simple problem to find the total resistance of this combination of resistors. We'll first work out the resistance for the parallel resistors, these two. We know that 1 over the total resistance is equal to 1 over resistor 1 plus 1 over resistor 2, which in this case is 1 over 10 ohms plus 1 over 15 ohms. Putting them over a common denominator of 30 gives us 3 plus 2. So 1 over RT is equal to 5 over 30. We must not forget to invert, giving us that RT is equal to 30 divided by 5, which is 6 ohms. As a quick check, it must be less than 10 ohms, which it is. Now for the easy bit, for the whole circuit, we can assume this is just a 6 ohm resistor, so we have a 5 ohm resistor in series with a 6 ohm resistor. So the total resistance is just the sum of those resistors, 5 plus 6, giving a total resistance of 11 ohms.